All right, greetings everyone. This is the second part of the video for section 1.6. So continuing on with our study of inverse functions and some of the properties about them and how to find them. Okay, so we've looked at inverses already in a couple of different manners. We looked at the inverse of a function given as a table, an inverse of a function given as a graph. We will look at inverses of functions given as formulas. However, a question that may be percolating in your mind right now is, does every function have an inverse? Are there some that don't? Interesting question, Cody. Well, let's take a look at this. So here we have a function f, and as per normal, we've got the inverses across the top, or sorry, the inputs across the top and the outputs across the bottom. And we're wondering whether or not this function has an inverse. Well, let's start by setting up a table for the inverse. So I'm going to mirror it down below here. So I am going to still have x as my input variable, but now my outputs will be f inverse of x, right? And we know that an inverse function switches inputs and outputs, right? So for the inverse function I'm trying to create down here, all of these outputs should become the inputs. So 4, 1, 0, 1, 4, 9. And then all of those inputs across the top will become the outputs down here, right? So I have a -2, -1, 0, 1, 2, and 3. And when I write the potential f inverse function like that, and you look at it, do you see, is that a function? Hopefully everyone just said a collective no, right? Because notice what we have here is that there are inputs that would have multiple outputs. So notice, for example, over here, we have that if we input 4, we get an output of -2. But way down here, we also see that if we input 4, we get a different value, right? We get 2. And that's not okay in a function. We also see a similar thing here. If we input 1, we get an output of -1. But here, if we input 1, we get a +1. So this is not a function, right? And so what that tells us is this original function back up here in the table, that function does not have an inverse. So the answer here would be no. Okay, so why does it not have an inverse? Why is this function not invertible, is what we say sometimes? Well, do you notice anything about the outputs in this function? Yeah, they look like they are repeated down here, right? So for example, I see 4 here and 4 here, 1 here and 1 here. So we have multiple inputs that go to the same output, which means this function is not what? Right, it's not one-to-one, okay? So our big takeaway here is that in order for a function to have an inverse, it must be a one-to-one function. Now, if you're given a function as a graph, right, how can we tell whether or not it has an inverse? Well, that's the same as asking, how do we tell whether or not it's one-to-one? And hopefully we all remember that's where we use the horizontal line test, right? The horizontal line test tells us if a function is one-to-one. Okay, so let's look at domain and range of an inverse function. Again, keeping in mind this idea that inverse functions reverse inputs and outputs. So we're told that we have a function y equals f of x that's one-to-one. It has a domain. Recall, domain is a set of inputs. So domain is x greater than 2. And a range, where the range is a set of outputs of y less than 1. So then we need to find the domain and range of the inverse. So how would we do that? Well, first of all, also I should point out, they told us the function is one-to-one, so we know it has an inverse. Now, how are we going to find the domain of the inverse? Well, we again remember that inverses switch inputs and outputs. So in the original function f, what is our range or our interval of outputs? Well, we see that that is y is less than 1, right? So if we're going to do the inverse, that's going to switch those from outputs to inputs. So our range, or sorry, our range for our original function will now become our domain for our new function, our inverse function. And rather than writing y is less than 1, we're going to stay consistent with which variables are the inputs and the outputs. So here we'll actually write that x is less than 1. Okay. Similarly, if we want to find the range now of the inverse function, well, we know that the range of an inverse comes from the inputs of the original function, which means it's going to come from the domain there. So from the x greater than 2. But again, we're not going to use x because we're talking about outputs now, so we'll say that y is greater than 2 would be our range. Okay, so basically we just switched our domain and range for our inverse function because we know that inverse functions switch inputs and outputs, so we switched domain and range, excuse me. Okay, all right, let's talk about formulas or inverses from formulas now, right? So here we're given a function h of x equals 3x minus 5, and we need to find the inverse function, okay? Or a formula for the inverse. So first thing I'm going to do, just to simplify things, is I'm going to write this, instead of h of x equals 3x minus 5, I'm just going to write h equals 3x minus 5, just to simplify things, and I can see, you know, the x is my input, h is my output. And if we're trying to find the inverse function, well, we just spent a bunch of time talking about how inverse functions switch inputs and outputs. So what we can do here is switch the inputs and outputs, to switch the x and the h. So we can now rewrite this equation as x equals 3h minus 5. And again, that's because inverses switch inputs and outputs. But our original function was not in terms of h's, so it didn't have an h over here, it had an x. So we want to do the similar thing with our inverse, so we're going to isolate the h there. So we can do that similar as we did in our prereq practice, add 5 to both sides here, end up with x plus 5 equals 3h. And then to get the h alone, divide by 3 on both sides. So we'll end up with h equals x plus 5 over 3. And that'll be the formula for our inverse function. Now, you'll notice, or actually it doesn't say it up there, but recall that the original function was called h of x. And we talked about when we're trying to write the notation for inverses, we use that -1 notation, okay? So what we can do is write this as h inverse, so with the -1 there of x, equals x plus 5 over 3. Okay, and that'll be our formula for our inverse function. Okay, let's now do the second part of this problem. So notice that it has told us to evaluate h of h inverse of x and h inverse of h of x. So basically what we're being asked to do here is do some composition of functions. Okay, so stuff that we did in, I believe, section 1.3 or 1.4. So if we're going to do h of h inverse of x, okay, well notice here we've got h inverse, that's the function on the inside, which is this one down here. So we need to take that and plug it in for x in the original function. Okay, so this would look like 3, and then in the place of the x, we'll put in the function for h inverse, which would be x plus 5 over 3 minus 5 on the outside. And notice now when we go to simplify this, okay, Well, we have a 3 up here. Whoops, did not mean to do that. So we have a 3 on the outside here that we can write as 3 over 1. You also have a 3 in the numerator and a 3 in the denominator, so those can cancel. And so what we're left with there in that first spot is just x plus 5. And then there's the minus 5, but notice the plus 5 and the minus 5 will cancel out. And we're just left with x. Okay? So that's what we get when we do h of h inverse. Now let's look at what happens if we do it the other way around. So now let's do h inverse of h of x, which means now the original function, h of x, is 3x plus 5, will get plugged into the inverse function. So what that'll look like then is, not that. So in the place of the x in the inverse, we'll put a 3x minus 5. Then we can do plus 5 there, all divided by 3. Notice on the top there, there's nothing outside the parentheses to distribute, so I'm going to get rid of those. And so we would have a 3x minus 5 plus 5. So the minus 5 and the plus 5 can cancel out. And so we're left with just 3x over 3, which those can cancel, those 3's. And notice now what we're left with again is an x. Okay. So notice that regardless of which way we did this, if we did h of h inverse or h inverse of h, we got x each time. And remember, x is one of our toolkit functions called the identity function, right? So here's the moral of the story, is that if you have two functions that are inverses of each other, this will always happen. If you compose the inverse function into the original function, you'll get x, and if you put the original function into the inverse function, you'll get x as well. The way, or why this can be useful for us, is it can be a way to help us try to determine if two functions are inverses of one another. So if you're just given two functions and asked to determine whether or not they're inverses, you can do this composition of functions. Now you need to do it both ways, so you need to do both of the things we did here. So plug the inverse into the original and plug the original into the inverse. And if you get x each time, then you know that they are inverse functions. Okay? All right, one more. So now we're asked to find a domain in which this function w of x equals x minus 3 squared is 1 to 1, and then use that to find an inverse on that restricted domain. Okay? Well, let's first draw a picture of this graph. And notice x minus 3 squared is a transformation of one of our toolkits. Which toolkit is it a transformation of? Right, it would be a transformation of the quadratic. And because that minus 3 is on the inside there, right, with the x, that means how has it been transformed? Right, it's been shifted 3 units to the right. Okay, so the graph then is going to look like a parabola or a quadratic shifted 3 units to the right, which means rather than having the little vertex at the point 0, 0, it'll be here at 3, 0. It'll look something like this. Now notice, first of all, is this function, does it have an inverse? No, it doesn't. Why not? Because it's not 1 to 1, right? It does not pass the horizontal line test. However, could we cut off some piece of the graph here? So that's what we mean by finding a domain or restricting a domain, so that we did have a 1 to 1 function. Well, it kind of looks like to me, if I cut off the left-hand side, so that over there, what's left should be past the horizontal line test, right? So that right-hand piece there. So it looks like that would give us a 1 to 1 function. Sorry if there's commotion in the background. My dog is being very annoying right now. Okay, so our domain here, we've taken off that left-hand piece, so it looks like we're just looking at a domain of 3 to infinity, and I'm including 3 because it's a little point along the horizontal axis there. And now that we've restricted the domain, we can go ahead and find the formula for our inverse. Okay? So again, we're going to rewrite this as w equals x minus 3 squared. Switch the inputs and outputs. Over here. Get in bed. So that we have x equals w minus 3 squared now. All right. Then we have to solve for w. And notice this is also very similar to one that we did in our prereq practice. So we need to undo the squared here first because it's on the outside there. Take the square root on both sides, square root here. And then remember, we take a square root, we do a plus or minus. So the squared and the square root cancel on the right-hand side. So now we have plus or minus square root of x equals w minus 3. And then we finish by adding 3 to both sides. So we get w equals plus or minus square root of x plus 3. And then in a function, we can't have plus or minus because that would give us multiple outputs for a single input. So we have to choose one of those, the plus or the minus. And which one are we going to use in this piece, do you think? Well, we used the right-hand side of the graph here, which is kind of like the positive side of the graph, or the part where it's increasing, right? So for the inverse there, we're just going to use the positive. So our inverse function here will be w equals positive root x plus 3. Whoops, darn it. Hit the wrong button again. Okay, so that would be our final answer. All right, thanks for watching. That's all for now.